Hello, and welcome back to the Quantum Networking channel by Aliro Quantum. If you're joining us for the first time, I have some helpful resources to highlight for you. First, if you have questions during the presentation, please send those questions to us anytime through the Ask a Question box located below. I'll be monitoring questions throughout our time together, and we'll answer as many of them as we can at the end of the presentation. You can download slides from today's presentation, as well as a quantum networking solution brief at any time by clicking the Attachments tab below. We also have a white paper for you about real-world quantum network deployment available for download. And lastly, this webinar is being recorded. It will be available to view on demand following today's live broadcast. I'm Emily Carter. I'm the community manager at Aliro Quantum, and today I'm joined by Michael Cubeddu, co-founder and VP of Research at Aliro Quantum. And today we're going to dive into the use of satellites in quantum networking. Welcome to the Quantum Networking Live broadcast, Mike. Thank you so much for being here today.
Thanks for the introduction, Emily, and thanks to everyone who's tuning in either live or watching the recording. This is a very exciting topic, lots to cover here. Quantum networking with satellites. This is arguably one of the most multidisciplinary topics we can cover. Quantum is already very multidisciplinary, but when we bring satellites into the picture, it becomes even more so. So depending on your background and where you're coming from, some of you may be familiar with quantum technologies, quantum communication. Others may be more familiar with satellite infrastructure and telecommunications and classical networking. And this technology marries the two. So I'll try and give an overview of existing infrastructure, but also how we move forward into using satellites for quantum networking. Okay, so here are some things you can expect to learn from today's webinar. As I mentioned, I'll start with an overview of today's satellite communications systems for classical networking applications and how we use those in everyday life. Then I'll move into how we can use satellites for quantum networking, so for entanglement distribution, for secure communications, and other applications as well. Satellites do play a pivotal role in scaling quantum networks. So as we build towards that first picture you saw on the intro slide, that global quantum connectivity, the quantum internet, that's what we're working towards. And satellites play a key role in scaling up quantum networking technology. Then I'll touch on quantum satellite deployments across the globe, what has been done, what is planned, and a little bit about recent advancements in technology and a future outlook of open problems and obstacles we need to overcome. And I'll end with a little bit about some strategic considerations, both for businesses and governments. So let's jump right in. So we use satellites in everyday life, whether we realize it or not. Likely you're using a satellite to receive some of the packets from this webinar stream. In today's digital society, we really rely on global connectivity of devices, and satellites are critical in providing that global connectivity for almost everything: voice, text, internet, TV, radio, Wi-Fi, online banking, financial transactions, military and defense applications, Internet of Things, science and metrology, for environmental monitoring, for imaging, for weather forecasting, for GPS. So if you've used Apple Maps or Google Maps recently, you've used a satellite. So we rely on this infrastructure critically, and we use it in our everyday life. So let's dive a little deeper into how these satellite systems work in today's world. So I'll start with an overview of a typical 5G satellite communication system. There's no quantum here. This is all a classical application, but just to get a refresher or a brief on how these satellite communication systems work. Every satellite communication consists of 3 stages, broadly. There's the uplink stage, in which the signal is transmitted from the ground, from Earth, to a designated satellite. So if you're in an urban area, for example, you might be communicating with a cell tower, and that cell tower is responsible for doing the uplink to a designated satellite. That signal, as it traverses through the atmosphere, may weaken, may degrade, and we move into the critical second stage, which is called the transponder stage. And this is a stage in which a satellite does what's called signal amplification. So it can boost the strength of that signal after it was weakened. And it might do some necessary frequency change of the signal. And from there, that satellite may communicate with another satellite in orbit. But eventually, it has to get back down to the other node. And so that downlink can communicate from the satellite to a designated ground station, or it can be a downlink to an aerial asset, such as an airplane. So satellites leverage different frequency bands and beam types. So I'll touch a little bit about what these frequency bands are used for, the typical applications, and the typical traffic they carry. So satellite and microwave telecommunications typically operate in the 3 gigahertz to 30 gigahertz regime. And you can see the band here. So the L band at the left here, it's a small band, but it carries traffic typically for applications for radars, for GPS, for Internet of Things, but also maritime and aviation applications. As we move to the right in the S band, it's twice as big. And the S band typically carries traffic for applications in shipping, in aviation, and the space industry. And something I think we've all come to love recently is airplane Wi-Fi. This is a good application of S-band traffic. As we move into the C-band, this is a lot of satellite TV traffic and also responsible for raw satellite feeds, so satellite imagery. And the biggest band that is used is the Ka band. The Ka band is carrying the majority of our satellite internet traffic, specifically for high bandwidth and high speed applications, such as video calls and streaming an Aliro webinar. So there are different frequency bands and beam types that I just spoke about, but there are also different orbits for different applications as well. So we'll start with the lowest orbit, what's called low Earth orbit. And so the low Earth orbit, or LEO orbit, is ranging anywhere from 160 kilometers to 2,000 kilometers above the surface of the Earth. The orbit time for a LEO satellite is about 90 minutes. And these satellites typically have a 5 to 7 year lifespan. If you're familiar with Starlink, they deploy a bunch of low Earth orbit satellite constellations to enable global coverage. As we move into medium Earth orbit, this is a larger range that can range anywhere from 2,000 kilometers to 35,786 kilometers. That sounds like a contrived number, but it is actually relevant, and I'll touch on it when I talk about the geostationary orbit. But the medium Earth orbit time is anywhere from 2 to 8 hours. And again, it lies between this low Earth orbit and the geostationary orbit. So at geostationary, all of the satellites in geo are either exactly 35,786 kilometers or very close to that distance above the equator. These geo satellites have much longer lifespan, anywhere from 15 years onwards. And the critical property of geo satellites is that when they travel in the same direction as Earth's rotation, they actually have a fixed position in the sky. So for any ground station that's communicating with a geostationary satellite, there's no fancy tracking that needs to be done here because the satellite is in a fixed position. But they all lie in the sweet spot of just under 36,000 kilometers above the equator. As we move further and further from Earth, there are other orbits to consider: the high Earth orbit, as well as the highly elliptical orbit. And these satellites can take anywhere from days to weeks, sometimes even months, to orbit Earth. With the elliptical orbit, there's also different distances from Earth that the satellite will cover. So at certain times in the orbital period, it will be closer to Earth, and at other times it will be much further. And these all have different properties for communication latency, for signal strength, and because of that, they host different applications. So, as I mentioned, the low Earth orbit, to get to global coverage, so if we have an application that requires global connectivity, we're going to need a lot of low Earth orbit satellites. And the reason for that is because they're closer to Earth, they have a relatively small field of view of Earth. So we're going to need a constellation of them to get to global coverage. That being said, because they are closer to Earth, they're extremely low latency. So the signals can traverse to and from Earth and the satellite much quicker than, say, medium Earth orbit or geo orbit. So typically, the application profile you see for low Earth orbit is telecommunications, so internet, 5G broadband, maritime applications, Internet of Things, emergency response systems. As we move further and further away from Earth into medium Earth orbit, this lies in a middle ground between the geostationary orbit and low Earth orbit. And there's a trade-off here, right? So we have reduced latency compared to geostationary, but also less required, fewer satellites required to get to global coverage than, say, a low Earth orbit constellation. Typically, medium Earth is used for GPS systems, which really under the hood is a timing system. So a lot of position, navigation, and timing applications here for medium Earth orbit satellites. Sometimes medium Earth orbit satellites are used to provide internet services to remote areas. The geostationary orbit, as I mentioned, because it has this fixed position in the sky, it's really suitable for more permanent communications links. Their field of view is about a third of the Earth's surface, so we don't need many geostationary satellites to get to global coverage. The application profile of geo orbit, we typically see applications like global imaging, global mobile communications, broadcasting, weather forecasting, and also geosatellites serve as a GPS reference for the other medium Earth GPS satellites. And as we move further and further away into high Earth orbit and highly elliptical orbit, we get into more applications that involve a global view of Earth, right? So Earth monitoring, but also because it's further away, we have better vision into deep space. So there are sensing applications, deep space exploration, astronomy and science experiments, things like that. So point is there are different orbits and different frequencies, each which carry different properties and application traffic. Just to give a quick statistic from earlier this month, as of January 3rd, there were 8,377 active satellites orbiting Earth. The vast majority of them are in low Earth orbit. And the reason for that is, as I mentioned, to get to global connectivity, we need a constellation of low Earth orbit satellites. So there's a large density of satellites in low Earth. It's actually becoming somewhat of a worry, not too serious now, but in the medium to long term, we have to consider space debris because there are so many LEO satellites, and once they are inactive or decommissioned, they are debris just floating in low Earth orbit. So that's something we have to consider as an industry. Okay, so the vast majority of satellite communication systems leverage the radio frequency band. They are more reliable. They're better for longer distances. They can penetrate through atmospheric conditions, clouds, rain, etc. If I have a Wi-Fi router in the other room behind me, I can still get Wi-Fi because it can pass through walls. That being said, recently free space optical communications have garnered a lot of interest for satellite communication systems, both in classical networking and telecommunications, but also with quantum. And the reason for that is because optical communications, the optical spectrum, has very different properties than the RF spectrum. The hard constraint with optical communications is that it does require line of sight between the two endpoints to communicate. So it can't pass through a wall. It is more sensitive to atmospheric conditions and physical obstructions. However, it has reduced interference with other electromagnetic signals, and we can get much higher data rates with optical communications links. So there are certain application profiles that we can consider that are more suitable for the optical domain than, say, the RF domain. And these optical applications are typically for very high bandwidth, high throughput requirements, shorter to medium range distances with a direct line of sight. So there are certain applications that the optical spectrum is great for, and there are other applications in which the radio spectrum is more suitable. And the reason I bring optical spectrum up is because that's what we're going to be using for quantum communications. So hopefully that's a good transition into the quantum part of our talk now, now that we have had either a refresher or a quick 101 on today's classical satellite communication systems. Now let's move into how we can leverage this technology for quantum communication. So satellite quantum communications really underpin a whole suite of very promising applications. And I really like this quote here from a survey paper called Advances in Space Quantum Communications. And it says that the second quantum revolution, which is a revolution we're living through right now, promises a paradigm shift. And that shift will deliver new capabilities, as well as performance enhancements in security, accuracy, and precision. So this infrastructure of satellite quantum communications will really impact a variety of fields. So yes, out of the box, we have the quantum native applications, say for a quantum secure communications, the quantum internet, entanglement distribution. We also have impacts in sensing. So quantum satellites have the potential to enable distributed quantum sensing, which will greatly impact position, navigation, and timing applications, say for optical clocks, navigation, etc. It will also revolutionize what we can do with science and astronomy and pushing the boundaries of fundamental physics forward. For astronomical applications like long baseline interferometry, but also detecting gravitational wave fluctuations, etc. And there are other fundamental experiments that this infrastructure can enable. So it's really going to touch a lot of fields of physics, communication, security, and science. Okay, so how do we do free space quantum communication? It's very easy. All we need to do is encode quantum states into optical signals. Seems easy enough. Why photons? Why optical photons? Well, photons have a set of unique properties that actually make them quite promising and a great candidate for encoding quantum signals for communication. Photons have multiple degrees of freedom suitable for quantum encoding. So photons have, for example, their frequency, photons have their polarization, etc. There are different degrees of freedom that we can use to encode our logical quantum states. These photons travel at the speed of light, which is great for communication systems. These optical signals, these photons, can be manipulated with optical components, and optical components are quite mature. You can buy them commercial off the shelf. You'll typically find a whole suite of them in your nearest university lab. But this technology is quite mature in how we can manipulate states of light. Photons are also promising because they are compatible with telecommunications infrastructure. So as we further develop this technology of quantum networking and quantum satellites, we don't want to rip and replace all of the great infrastructure that we spent a lot of time and money on. We don't want to rip and replace with new special quantum fiber. Let's leverage the existing optical fiber and networks in the ground. So we want to be compatible with existing infrastructure here, and photons serve as a great platform for that. Photons operate quite well at both cryogenic temperatures as well as room temperatures, which makes it a promising platform for space deployment. And I like to think of optical photons as sort of the universal language or medium by which quantum platforms can communicate. So there are many different quantum platforms out there. Even in, say, quantum computing, you have superconducting qubits, trapped ion qubits, cold atoms, etc. There are all these different platforms and architectures for implementing, say, a quantum computer, all with different properties. If we wanted different quantum platforms to communicate with each other, we should use optical photons. The reason for that is because they serve as the most promising interface with these separate quantum platforms. So for example, you can have a wavelength of a photon that's resonant, say, with a matter-based system. And so we can begin to explore these interfaces and connect a variety of quantum platforms together. So all of these properties of photons make it a very promising spectrum for encoding quantum states for communication. Okay, so how do we actually do the encoding? There's no one size fits all, no single recipe here for the best encoding. I will say the most popular encoding is polarization encoding. And here we're using what's called the discrete variable encoding. So we're encoding a quantum state into the polarization of a single photon. So if you look at the figure at the top right, here's an example encoding in which we encode the ground state or the zero state of our quantum state into the horizontal polarization of a single photon, and we encode the excited state or the one state into the vertical polarization of a photon. And if we do that, we can, for example, encode superposition states. So this is something that cannot be replicated with any classical system. So for example, if we wanted to prepare a plus state there that you see at the top right, we can encode that in, say, a diagonal polarization of a photon and or the anti-diagonal. So we can leverage superposition and entanglement via photon interference to create multi-qubit states. So this is typically one of the most popular encoding mechanisms. So that's using the polarization degree of freedom of photons, but there are other degrees of freedom that we can use to encode quantum states. So for example, there's what's called time bin encoding, or if you have heard of time bin qubits. This is really using the position of the photon in time as a dimension to encode our quantum state. So depending on when we expect a single photon to arrive at a certain place, that will determine what the photon state is. So for example, we can say an early arrival is the zero state and a late arrival is the one state. So we can use time as that dimension. We can also use space as another degree of freedom. So there are optical components that can manipulate the path by which a photon will travel in space. So we can use, say, different physical paths in space to encode our states. And we can use what's called presence or absence decoding to detect what kind of state we have. We can also leverage frequency encoding using the spectral band. So for example, here we have linear optical quantum computing, which is a proposal out there for actually using frequency encoded photonic qubits for scalable quantum information processing. So the point is here, there's no right way or single way to properly encode quantum states into photons. There are many levers we can pull. There are many degrees of freedom we can leverage of a photon to encode quantum states. They each have trade-offs. And I'd like to touch on wavelengths a little bit here, because wavelength selection is critical as we're building these space-based quantum communication systems. The wavelength selection is critical because they come with trade-offs, right? So depending on the system we're trying to set up, what are the distances we're talking about between satellites and ground stations, between ground stations on Earth, et cetera. We have to think about crosstalk as well. So is there other traffic in a nearby wavelength regime that may interfere with my quantum signals? We also have to consider resonance with matter-based systems. So if we want to communicate using these photons to, say, a matter-based quantum system, there are certain wavelengths that are resonant, say, with that type of matter or ensemble. There's also practicality considerations out there, right? What technologies and components are out there that are compatible with a certain wavelength regime, and we have to consider, all the cost factors and form factors as we're deploying on a satellite. There are two, schools of thought, if you will, of how to encode quantum states into photons. So, typically the formalism that most people are familiar with is discrete variable encoding. So if you've ever had an intro to quantum mechanics, or you've maybe learned a little bit more about quantum computing, you hear these words like gates. You hear words like computational basis, zeros and ones, etc. It's a very discrete system. We're using a Hilbert space that is discrete. Whereas in continuous variable encoding, we're using continuous variables to encode our quantum states. So for example, we can use the quadrature amplitudes of an electromagnetic field. We can use the amplitude or phase as dimension by which we encode our quantum information. In continuous variable encoding, so we're still using light here, we're still using photons, but it's a different kind of light and a different way to process it. So in continuous variable encoding, we're using Gaussian states, we're using squeeze states of light, sometimes coherent light. But the idea here is that in continuous variable, our Hilbert space is infinite. So the observables, when we measure a quantum system that's continuous variable, those observables can lie on spectrum. Whereas in discrete variable encoding, our observables are at discrete levels. So for example, when we measure a discrete qubit, we get, say, either a 0 or a 1. In terms of state preparation and measurement, so in discrete variable encodings, we use standard quantum logic gates for manipulating these states. These are logic gates that you typically see, say, in quantum computing to manipulate these states. How do we measure a discrete variable system? We use single photon detection. So we're just detecting the presence or the absence of a photon at a certain time, and that will give us information as to which discrete observable we are measuring. In continuous variable setups, the state preparation and manipulation of these states is done with non-Gaussian operations, things like squeezing, displacement operations, etc. And the measurement is very different than a simple, single photon detector. Continuous variable systems leverage what's called homodyne detection. And these homodyne detectors have been around for quite some time. It's a relatively mature technology. And they're able to produce observables that, again, lie on this spectrum. It's not just a 0 or a 1. It can be measuring, say, the amplitude of a certain field. In terms of the protocols, there's a lot of overlap here. I mean, both encoding schemes can support a variety of common protocols, say like quantum key distribution. But there are other applications that are, say, better suited for one type of encoding versus another. So, for example, recently it's been shown that continuous variable encoding may actually be beneficial for daytime environments when communicating over free space. So I said it was easy, right? All we have to do is choose our favorite encoding scheme, and we're good to go. No. So there are many physical challenges and also technological challenges that we have to consider when deploying a quantum-enabled satellite. So on this slide, I've kind of categorized the challenges. So we need our system to be operational, right? It needs to be practical as well, and have a good return on investment. Okay, so how do we get the system up and running? How do we get it operational? Our components need to be as low swap-C as possible. So what is swap-C? Swap-C stands for size, weight, and power, and cost. So any technology, any piece of hardware that we're deploying on a satellite, right? Satellites are expensive, and every single gram of hardware is associated with fuel cost, right? So we need to get that size, weight, and power, that form factor, as low as possible. We also need these satellites to be operational, well beyond their launch. So I mentioned earlier that low Earth orbit satellites typically have a 5 to 7 year lifespan, right? So we need our quantum hardware to have that same lifespan. In addition, we're not going to be able to have a team of PhD students or postdocs working to recalibrate these systems and fix bugs, right? They're up in space on their own. So we need to have automated self-calibration. We also need our system to be reliable, right? And we have to take into account all of the factors that come with a space deployment on a satellite. We have to think of the effects of radiation and how that may degrade certain quantum components. We have to consider large temperature fluctuations as the satellite is orbiting Earth. We have to consider vibrations, and we have to maintain a robust synchronization system to make sure our satellite system is reliable. We need our system to be available, right? And as I mentioned, with optical communications, we need that line of sight constraint, right? So we need to maintain that line of sight, and we can only run, our communications once we have that. So we need efficient pointing and tracking systems to make sure that the signals are properly going to the designated ground station or satellite. We need proper alignment of all of the optical components therein. And that's really important because we need to be able to capture the relevant signals and eliminate as much noise as possible. In additional, orbital coverage is important too, depending on the application, right? We have to consider what kind of coverage we need. Are we talking about a global coverage application, or are we okay with a single low Earth orbit satellite in which we may have only a dozen minutes a day, say, of available quantum communication links. At the physical level, the signal processing is a big challenge here. We have to consider how the effects of the atmosphere on the signal. So how the signal may scatter, may attenuate as it's passing through, say, clouds, fog, rain. The signal can scatter, it can diffract. We also have this bug and feature of the no cloning theorem. So this is a theorem just for quantum signals, in which case, it really implies that we cannot amplify the quantum signal. So with classical signals, it's easy. If it gets a little weaker, we can just bump the strength up of the signal and send it along to the next hop. We cannot do that with quantum signals. So they're very fragile already, and we really need to take care of them. So every photon counts. Okay, so as I mentioned in the introduction, satellites play a pivotal role in scaling quantum networking technology. So here's an example of how satellites can be leveraged to distribute entangled pairs of photons to very distant ground stations on Earth. So if we want to work towards a global quantum internet, that will require a combination of both terrestrial networks on the ground and space-based segments here. And the idea is that there are a set of optical ground stations which are responsible for receiving the photons from, say, a photon source that sits on the satellite. In this example here, on the right, I'm showing entanglement distribution with a terrestrial repeater here. So say we have two ground stations on Earth that we want to connect with entanglement. They're very far apart and too far apart for a purely terrestrial link. So how can we get entanglement to those two ground stations? In this example here, we have two satellites. Each of them have an entangled photon pair source on them. So they each emit a pair of photons. One of them goes to the end node and the other goes to this terrestrial repeater node. And this middle node here is responsible for capturing those incoming photons, one from each pair from the different satellites, and doing what's called photon interference or entanglement swapping. This is a process which effectively transfers the entanglement to from two piecewise entanglements, kind of stitched together into the long-range entanglement. So that's how we can deliver entanglement to very distant ground stations using satellites. There are different architectures we can consider here. In this case, we had two satellites with downlinks. There are uplink architectures in which the ground stations are the ones emitting photons up to the satellite, in which case the repeaters would have to rely on the satellite. So there are trade-offs here and different architectures we can draw up. I'd also like to highlight the last point here that there's some recent interest and potential for high altitude UAVs as a way to more effectively connect satellites with these terrestrial quantum networks. Okay, so let's talk about what has been demonstrated and what's coming. So the application for quantum networking that is arguably the most popular or in the most demand is quantum key distribution. And the reason for that is because it has the potential to provide truly quantum secure communications. So there was a landmark experiment done in 2016 with the Messias satellite that was launched by China, and they were able to demonstrate entanglement between two distant ground stations in China, about 1,200 kilometers apart. In 2017, they used this satellite to do the first quantum encrypted virtual conference between Vienna and Beijing. So really, really cool application, and this was it made a big splash in the quantum community, but also the broader science community. It made the front cover of Science here. As you can see here, in the bottom picture, China is really investing a lot of money and resources into developing their quantum communications infrastructure, with their terrestrial footprint being extremely large here, but also, really leading the way in space-based quantum satellites. Okay, so let's talk a little bit about architectures for scaling quantum networks using satellites. And I think really, the central question that really simplifies it is, I have two ground stations I want to connect with quantum entanglement. They're very far apart. Should I use a space-based link using satellites? Or should I use a terrestrial repeater chain just using fiber in the ground? Um, and here on the figure on the right, that addresses this exact question. Depending on the distance we're talking about, depending on the throughput you need, terrestrial repeaters may be better in some regimes, but in others, satellites are really the way to go. There are different architectures we can consider. So the one I showed a couple of slides ago was showing two downlink architectures where the satellites have the photon sources and they're sending them down to ground stations. You can imagine, a constellation of these satellites in low Earth orbit where you have downlinks, but also links between satellites, so inter-satellite quantum communication, also ground-to-ground free space optical communications where we just have, telescopes on the ground communicating directly with a line of sight. And as I mentioned, the quantum internet will be a combination of both free space, space-based links, and terrestrial networks. There is no one-size-fits-all architecture here. It really depends on the application. So the application informs the architecture. The application requirements really inform what's the best link and hardware setup we need. So the application may require a certain coverage. So are we talking about full global connectivity? Are we talking about regional connectivity? If it's, say, an application for a metropolitan region, then we should be fine with just terrestrial networks. But if we're talking about, doing quantum secure communication, from London to New York, then maybe a satellite link is more suitable. So the distance matters, the coverage matters, the key rates will matter. If we're doing something like quantum key distribution, we need to know what throughput we need, what uptime, network uptime we need, and also the cost. So all of these application requirements, inform the architecture. But we want to build scalably. We want to build towards this end vision of a global quantum internet. We need to be prepared for advancements in technology. So, for example, one-way repeaters. So we need to build these systems with not only the application in mind, but also, what we can expect from technological development in the coming years. Here's a little bit more about the application. So we spoke a little bit about quantum key distribution, which garners a lot of interest and demand across the world. But there are many other applications that quantum satellites will enable. The point is higher orbits enable new applications and different application profiles. So, at low Earth orbit, we can, that's been demonstrated. We can do that. We can use constellations of low Earth orbit satellites to get to global quantum connectivity. But there is still, a value for, really pushing this technology further and further. We can, as we get further and further from Earth, we can enable applications really pushing the field of fundamental physics forward, right? So we can start doing tests at the intersection of quantum physics and relativity, and we can work towards developing a theory for quantum gravity. So these are, really critical questions about the nature of our universe. And, quantum satellites really serve as a promising platform to test these things out. So here's a timeline of different global efforts for quantum satellites. The first free space quantum entanglement distribution happened back in 2005, over 13 kilometers. This was a terrestrial demonstration. And then we move all the way to 2020, and we can see, in brown here, how many CubeSat launches have been done. CubeSats, these are small, low Earth orbit satellites. This really kind of highlights the critical role that CubeSats play in not only quantum communication, but also classical communication systems. So in blue here, we have demonstrated milestones, which you can see. We've demonstrated quantum teleportation. We've done a bunch of quantum key distribution experiments, etc. In red here, you see the proposed missions kind of going forward. One point I'd like to make here is that it takes a village, and most of these projects are, it's a conglomerate of collaborators, both with public participation from government agencies, also private companies, startups, and bigger companies too, satellite companies, but also universities and academics. So it really takes a village to get something like a quantum satellite demonstration up in space. I'd just like to highlight here a couple space-based demonstrations for quantum satellites. So there's the KeySat project, which is driven by the Canadian Space Agency. The launch is next year in 2025, and the goal of KeySat is to launch 3 low Earth orbit satellites to study, demonstrate, and validate space-based secure communications. So this really has the encryption angle to it. There's the Eagle-1, which is launching this year, the European Space Agency. QKD-SAT was launched last year by ARCIT and the collaborators in the UK. And as I mentioned earlier with the MISSIUS demonstration back in 2016, China is going full steam ahead. There are other evolved experiments that they have done and have planned. So there's the Shenzhou 16, the follow-up project launched last June, and they're planning to launch a geostationary satellite in 2026. Singapore is also very active in this space with the National University of Singapore's Center for Quantum Technologies in collaboration with a company called Spectral. They have a project called Spooky Sats, and that took inspiration from spooky action at a distance, which is, Einstein coined that phrase. So they launched in 2018 and 2020, and the goal was to demonstrate entanglement generation on a satellite. There's a collaboration between Oak Ridge National Labs and University of Illinois, Urbana-Champaign. And, this collaboration was really to kind of study the analytics of this technology, to do emulations and simulations to demonstrate how satellites could enable more efficient and secure quantum networks. The NASA Deep Space Quantum Link project, the goal there is to establish long baseline quantum link, potentially between the Lunar Gateway space station and nodes on Earth or near Earth. And finally, I will talk about QDICE. This is a project led by Thales Alenia Space, but is really a large conglomerate of collaborators in both public sector, private sector, and academia. And for QDICE, the goal is to launch 2 sources for QKD, one for discrete variable encoding and one for continuous variable encoding, to kind of explore the trade-offs there with the different encoding mechanisms. Also studying the effects of quantum random number generators, developing satellite pointing acquisition and tracking systems, and using a 5G communication system to do the necessary post-processing for quantum key distribution. So each of these projects, and forgive me, this is not exhaustive, and I apologize if there's someone attending that I didn't mention their project, but each of these projects have a different sort of viewpoint or flavor of space-based quantum communications. Some of them are studying, the effects on secure communications and encryption. Others are, studying the effects of, encoding mechanisms, trying different photon sources for continuous variable, discrete variable, etc. So I'd like to kind of wrap up with some recent advancements and a little bit about, where we're going from here. So photon sources are critical in any quantum communication system. Right now we have demonstrated entangled photon pair sources deployed on satellites back in 2016 with the MISSIUS satellite, for example. So where do we go from there? So in the near term, medium term, entangled photon sources should be developed to leverage multiplexing. So for DWDM technology, for broadband sources, let's leverage the frequency band. And then as we move further and further, let's move from just entangled photon pairs to hyper-entangled states, multi-dimensional entanglement. And then from there, we can develop protocols with fewer and fewer trust assumptions on nodes. And something that's really important is we need to do co-development between photon sources and quantum memories. So that interface is extremely important to make a scalable quantum internet. We need to have our sources, efficiently interfacing with our quantum memory systems. Photon detectors are also extremely important. We need to detect these quantum photons, right? So if we're mounting detectors on satellites, as I mentioned before, radiation is something we have to think about, and radiation does have an effect and does degrade the quality of our photon detectors. As I mentioned earlier, we need these systems to be reliable and to be self-calibrating and self-healing. So here's I wanted to highlight a project from a couple years ago out of IQC and with many other collaborators, where they studied silicon avalanche diodes, photodiodes, for photon detection. And they actually used an in-orbit laser annealing approach to self-heal from radiation damage. So this is, technologies like this are really important for kind of pushing the boundary to the next generation of photon detectors for satellite deployment. Quantum memories are extremely important as well in scaling quantum systems and quantum networks. I'd like to highlight a few different promising platforms for quantum memory. So there's warm vapor, there's laser-cooled atomic systems, cold atoms, rare earth ion-doped crystals. These are all different ensembles for being able to capture that photon and store it and retrieve it on demand from the quantum memory. And quantum memory really enables a whole suite of protocols that you can't do without this storage capability. And I'd also like to mention photonic integrated circuits. And photonic integrated circuits are a very promising technology because of their footprint, and especially when we're talking about quantum satellites and deploying this technology in space. Photonic integrated circuits are great because they're on a chip and they're light, they don't consume a lot of power, and they have all the optics functionality built in. So this is a relatively new technology that we have seen some recent advancements and a lot of investment in startups in this space to really increase the footprint of functionality that these chips have for quantum networking. And that being said, a lot of that work is being done in quantum computing land. So photonic quantum computers, they need this functionality as well. So if they're able to push that frontier forward on the computing side, then they may very well serve as great candidates for a quantum satellite. So with that, I'll end with a short call to action here. Quantum satellites are the next frontier. It's a very exciting multidisciplinary technology. It's really going to take quantum networking from these small local area, metropolitan scale terrestrial networks into eventually the global quantum internet. And we're going to need quantum satellites to do that. Now's a great time to shape your quantum strategy. If you're a telecommunications company or if you're a satellite company, it's very important to be aware of this development, also as a way to differentiate yourself from your competitors. As I mentioned, there is, to get a project like this going, it takes a village, and it takes partnerships and collaborations between, industry, academia, as well as the public sector. And there are national security implications with this technology. As I mentioned, quantum satellites can enable better military applications for position, navigation, timing, for also sensing and doing metrology. Also the cybersecurity angle. So there is a political game being played across the globe to really move forward this new space race. So with that, start your quantum networking journey now. Please contact us. And thank you all so much for attending this webinar.
Mike, thank you so much for this presentation. Satellites have played a huge role in the classical internet. They have a role to play in quantum networks as well. And now we have some questions for you. So folks, if you have questions, please add those to the queue. If there are any questions that we can't get to during the time we have today, we'll follow up with you individually after this session. So our first question is asking about speed and latency. And so quantum networks have very specific timing requirements since that entanglement can degrade quickly. So what is the expected performance of satellite-based quantum networks in terms of that speed and latency?
Mm-hmm. Yeah, great question. It's actually a very hard question to answer without some kind of a simulator or something, because there are so many factors here we have to consider. What is that latency? If you're doing something like quantum key distribution, you really want to know, okay, what's my key rate? How fast am I getting these secure bits? It depends on a lot of things. It depends on, mainly where your satellite is. If you're using a satellite QKD system, your latency is going to be, very low if it's a low Earth orbit satellite, because the satellite is closer. Our signals are getting to and from Earth a lot quicker than, say, a geo satellite. That being said, that comes with trade-offs. The lower your orbit is, the less time you have for an available window to communicate with that satellite. You have to wait for it to pass into an acceptable field of view. Again, we need that line of sight connectivity, so we need efficient tracking mechanisms to make sure we can have that link when it's available. So yeah, latency is one way to look at it. Yes, it's an important metric, but if I have low latency, but my link is only available, a dozen minutes a day, that's a trade-off, right? So there are many things to consider, and it's important to be equipped with all the tools to shape that strategy and that architecture, like, say, a simulator.
Excellent, thank you for that.
Mm-hmm.
So this next question, and you touched on some different quantum satellite launches, some different quantum satellite projects that have been happening. And
Mm-hmm.
This next question is asking about US satellites in particular. Has the USA launched any satellites to support nationwide QKD? And if not, is the US planning to launch these kinds of satellites?
So there are programs in NASA. I would say relative to other nations, NASA's projects have longer timelines and are attempting to solve a lot of problems in one big contract and one big project on a single satellite. So it's going to take a while, but NASA does have demonstrations in lab. They've I've seen it in person at some of their labs, that they are working on this technology, not only on the satellites, but also on the ground stations, which are really important. It's not just as important as the satellite deployment. We need to be able to effectively and efficiently capture these signals from the satellites. So they're doing a lot of work, both on satellites, but also ground stations. A lot of the lunar projects that are launching this year, next year, they do have a lot of optical technologies. Again, they're for classical applications. That being said, a lot of the optical infrastructure that these satellites have, say for the Lunar Gateway or the laser communication system with the moon, they have a lot of the same componentry and infrastructure that quantum would require. So there will be some modifications that need to be made to make it quantum enabled. That being said, NASA is doing all the right things in developing that fundamental piece before we move on to quantum. So yeah, they are looking at it, and they do have launches planned for quantum satellites.
Excellent. That's great insight. We have another question for you. This is probably our last question. And this is really speaking into the different satellites for different applications that you were talking about. Is there an ideal satellite for quantum networks?
In my utopian vision, yes. I think an ideal quantum satellite is one that has a hyper-entangled photon source, so a source that's capable of preparing these highly entangled states with many output ports, so it can communicate with many other satellites and many other ground stations. It is equipped with very efficient detectors that are self-healing from radiation. It is equipped with quantum memories that can store quantum photons forever, and I can retrieve them whenever. And also, optical components for manipulating these quantum states. That's a lot to put on one satellite, and it's as I mentioned, a very utopian vision, but that's what we want to work towards. Having this quantum-enabled satellite.
Excellent. Excellent. Thank you so much, Mike. We are unfortunately out of time today. So folks, if you have questions that we didn't get to today, we'll reach out to you directly with answers. If you have questions while you're watching the on-demand replay, you can direct those to info@aliroquantum.com. Thank you everyone for attending the broadcast today. And Michael, thank you so much for sharing so many important insights around using satellites in this particular architecture of quantum networking.
Sure thing. Thanks for having me, and thanks to everyone who joined.